Good morning. Thank you for joining this session, and I'd also like to thank the institution for inviting me to speak to you today. I'm Bob Hinchcliffe. I've been involved in engineering since 1969 when I started a toolmaking apprenticeship at the ripe old age of 15. I've been involved in robotics and automation for many years, and probably for about the last 12 years I've been a member of the Council of BARA. I'm here to talk to you today about robot system integration. However, before launching into the main topic, I think it'd be useful to give you some background information on BARA, the UK market for robotics, and a comparison with Europe and the rest of the world. BARA, which is the British Automated Robot Association, has been the voice of automation since it was founded in 1979. It's a well-respected and recognised association. Our membership covers all aspects of the robot supply chain, from robot suppliers, integrators, suppliers of control systems components, mechatronic components, safety systems, and we also cover the academic world. We get involved in all sorts of activities such as education and promotion. It's vitally important that we try to introduce younger members of the population, i.e. while they're still at school, into the field of robotics and engineering. We take place in various conferences and seminars, and we are to be seen at many of the well-known exhibitions. We have relationships with EBA, the MTA, Gambika, the FDF, which is the Food and Drink Federation, and also PPMA, which is the Process and Packaging Machinery Association. We're members of the International Federation of Robotics and contribute annually to the sales statistics for robots. We also have interaction with the UK government, for example, the Department for Business, Energy and Industrial Strategy. So we do have a means of influencing government strategy on automation. There are many challenges facing UK manufacturing, particularly in the area of productivity. The Office for National Statistics did some research, and they've made a statement: 0.3%. That is the estimated average annual increase in UK productivity in the decade or so since the financial crisis. Clearly, to be competitive, we need to increase productivity. I think this statistic is rather shocking and gives a clear indication of the challenges which UK industry is facing. We've touched on the fact that there are certain challenges facing manufacturing in the UK. Let's have a look at some of them in detail. Productivity. Well, I think we've touched on that, and I don't think I've got anything more to add other than we need to do something to overcome the relatively low rates we are seeing. Brexit. We're probably all sick to death of hearing about Brexit. I won't touch on that. We know there are challenges. Hopefully we're starting to overcome them, but yeah, no more to be said. COVID-19, oh crikey, what a disaster that's been. Many manufacturing industries ceased production completely, others were just ticking over, yet in certain areas there's actually been a boom. So there are a number of companies who have ended up employing more people, increasing production, extending manufacturing facilities. So not an absolute total disaster, not good by any stretch of the imagination, but yeah, nothing else to add there, I don't think. Labour availability. Certain sectors are really struggling for labour. Perhaps a lot of it has been caused as a result of Brexit. A lot of European workers have simply gone back home and won't be returning. That's left a huge gap in many industries. Skill shortages. Yeah, I think the last statistic I saw was that we're up to 100,000 graduate engineers short in UK manufacturing. Clearly, a lot needs to be done to address that challenge. Culture. Many companies just don't help themselves with the culture they have. The approach on return on investment shown by some companies is that if they can't see a return in less than a year, they just won't make the investment. This is contra to the attitude in many European countries. Germany, for example, will take 3, 4, possibly 5-year approach towards return on investment. It just means that in the UK, many good automation opportunities are just totally overlooked and missed. Attitude to risk. Some companies are extremely risk averse, whereas if they ease that slightly, they could open up a whole new host of opportunities. Perception of robot automation. Yeah, it is often seen in many areas that robots are taking our jobs. This is a myth, really. It's been shown on a global scale that those companies that do invest in robots and automation, in fact, in the long run, do employ more people. Short term, there may be a slight dip, but as the competitiveness of the companies actually improves, they then win more business. As a result of winning more business, they need to employ more people. So, yeah, complete myth. Robots create jobs, they don't take jobs. The adoption of robotics and automation can have a dramatic effect on productivity. So let's have a quick look at the numbers of robots installed in the UK. The graph in front shows the number of robots sold by year. What we can see is that there's no clear trend at all in these figures. Everything is quite erratic year by year. The years where there's significant numbers, these particular years have been skewed by big investments into the automotive industry, which is by far the largest user of robots in the UK. I think one interesting figure is that in Q1 last year, there were over 1,000 robots installed, but again, this has been skewed by a significant investment by the automotive industry, and it looks as if the majority of those robots were actually installed before we started the pandemic lockdown in March last year. I think if we look at Q1 for this year, the level of robots is, as good as many years previously. That's even more incredible by the fact that we were still in the depths of the pandemic. So to achieve almost 500 robots in the first quarter, I think is actually a fantastic result. The International Federation of Robotics collects sales data from around the world and then uses it as a means of comparison. What they do is they calculate the robot density as the number of robots employed per 10,000 employees. So the chart in front shows for the non-automotive sectors a comparison of a number of European countries. Clearly, you can see at the left-hand side, no surprise there, Germany is at the forefront, utilising 195 robots per 10,000 people, whereas at the right, you can see that the UK comparative figure is only 46, roughly a quarter of what we see in Germany. This has obviously an effect on our ability to compete effectively and has a dramatic effect on productivity. So while we could beat some of them in the field of football, clearly not all of them, in the field of robotics and automation, we are getting thrashed. So if you thought the European position was bad, let's have a look at the global position. The global average is 113 robots per 10,000 employed. This is for all industries, including automotive. You can see that way out to the left, we've got Singapore up at 918. Now, working our way across all these major manufacturing countries, what you'll see is that the UK doesn't even appear in the top 20 on this chart. In fact, the UK only ranks 24th in the world with a robot density of 89 units. However, not everything is total doom and gloom. The automotive sector has obviously been a major user of robots and automation for many, many years. And over the last 9-10 years, what we've found is that productivity has grown within automotive quite significantly. Many companies there now produce 56% more per hour than they did in 2009. This really has come about as a result of major investments into new robotic and automation systems. What they've also found is that the introduction of new technology has also created thousands of jobs. Perhaps what we ought to do is learn from the automotive sector and apply those lessons into other manufacturing sectors in the UK. There was a study done recently by the Copenhagen Business School looking at automation, productivity and employment across quite a wide range of manufacturing sectors, and they compared quite a large number of EU countries and also Japan. Sadly, one of the main findings they found is that the UK was in the last place for productivity in almost every sector they looked at, which is obviously quite depressing. However, another factor which came out of the work they did was that if the UK was to adopt more robotics and automation, and if it became then as automated as the most productive country, then we would see over a 22% increase in productivity. The effect of that on employment, in short term, potential decrease, but longer term, an increase of nearly 7.5%. So if we go down the road of robotic automation, what benefits can we see? Well, we get better utilization of space and more efficient use of energy. Improved productivity as a result of increased yield, improved utilization of other equipment, better utilization of staff, taking them away from the dull, boring, repetitive jobs and putting them into places where they can add value. Consistent high quality. A machine will perform the same task time and time and time again, exactly the same, whereas human operators, they've got perhaps a better performance at the start of the day, they're wane towards lunchtime, pick up again after a break. So performance is up and down. So machines give you that consistent high quality. Also leads to minimised damage and fewer breakages, less waste and rework. Improved competitiveness. Flexibility, you can get quick changeovers. Product redesign can be taken relatively quickly. The robot tooling can be changed easily. Robot programs can be changed very, very readily. You can extend production hours. A robot will work 24/7. It can be lights on, lights off, the heating can be on, the heating can be off. It doesn't care, it will just keep on working. Improved health and safety. Yep, a lot of the repetitive jobs have got a potential risk of RSI, so that can be removed. Manual handling, manual lifting, there are dangers associated with that. More rewarding jobs. Yep, people working robots, programming robots, higher skill levels, much more satisfying. There's a saying attributed to Henry Ford: if you need a machine and don't buy it, then you will ultimately find that you have paid for it but don't have it. What he's alluding to there is that if you don't put automation in, you end up paying more for your piece parts. So in the end, you've actually paid what it would have cost you to buy a machine, but you don't have that asset at the end of it. Perhaps not a very wise decision. There are many opportunities for putting in automation in the UK. Applications such as machine tending, welding. There are very many very nice robot welding cells. Picking, high-speed picking, packing, palletizing, any type of task which is boring, repetitive, mundane, dangerous is a perfect opportunity for automation. Companies who put in automation do gain a really good competitive advantage. They could achieve better financial returns, which in turn means that they are more efficient, more productive, more profitable, which in turn leads to taking on more business, so they grow. As they grow, they give more employment opportunities, bring in more jobs. Once we've decided which of the automation opportunities we want to follow, we then need to consider which is the preferable type of robot to be used for the application. And at the moment, typically you could choose between either a collaborative robot or an industrial robot. Collaborative robots, commonly known as cobots, are relatively new into the market, but there is some strong interest being shown from certain manufacturing sectors. One aspect is that they can reduce the fear factor of installing robots. It is a type of robot which can be used collaboratively, working side by side with humans. It gives us great flexibility. They're relatively easy to install and use. They can be used for operations which require direct collaboration between humans and robots. For example, an operator could assemble certain parts of an assembly which require manual dexterity, which robots just can't have. They can then pass them to the robots, who can then take over and conduct other tasks on them, which are repetitive, boring, mundane. So typically cobots are used in areas where batch sizes are relatively low. Perhaps there are space constraints. There could well be situations where on a production line there just isn't enough room to put a physical barrier around a standard industrial robot. Where they form part of a process which requires human intervention, where payloads are low, most cobots have capacities of 10 kilos and less. There are a few available which have around about a 15 kilo payload, and I think there is one which has up to a 35 kilo payload, but the majority are 10 kilos and less. They are not as repeatable as industrial robots, so if an operation has got a repeatability requirement of more than about 0.1 of a millimeter, then cobots can be absolutely fine. Applications which are slower, they are not by any stretch of the imagination high-speed robots, because of the way they operate alongside human operators. Then there is an absolute requirement to keep the impact force on the human body as low as acceptable. So therefore, speeds less than 1 meter per second is all that can be used with a cobot. They're ideal for situations where a robot may be used on one production line. As soon as the process there finishes, They can be moved across to a different production line or a different location. So frequent redeployment and frequent reconfiguration of the operation are ideal scenarios for the use of cobots. Another feature is that the user or the end user more than often installs the robots themselves. They don't rely on a professional integrator. One absolute key thing which must be done is a risk assessment of the process. When you take delivery of a cobot, as soon as it comes out of the box and is powered up, it is inherently safe. However, as soon as you install an end effector or a tool onto the end of the robot and define what task it is doing, there is always the potential of danger. So therefore a full risk assessment must be done to ensure that the application is safe and you will comply with regulations. That is probably the most important thing to take away from this part of the presentation. When we start looking at typical industrial robot applications, you'll see that immediately the higher volume type of production scenario is very much where they are ideally used, where tasks are dangerous, arduous, dirty, repetitive. Again, these are ideal scenarios for industrial robots. Usually when robots are used in an industrial capacity, they're usually around a fixed installation, usually fully guarded with safety interlock doors, safety access switches, light curtains quite often used, the limited human intervention. It is possible to allow robot setters, robot programmers into the robot cells, but to gain access it's usually through a trapped interlocked key system or a coded fob. The robot is then put into a manual mode. It will not be possible to run it in an automatic mode. In the manual mode it will run at typically around about 10% of the rated maximum speed. The operator will be using a connected teach pendant with an inbuilt deadlock, so you know, they can work safely in close proximity to the robot. Payloads on this type of robot are typically much higher than you would use on a cobot. 10 kilos plus is not unusual. The maximum I'm aware of at the moment in terms of the payload is around 2.6 tons with a reach of about 7 meters. So that is one really large robot. Many industrial robots are down around about the 3 kilos, 5 kilos payload, and typically these will operate at a relatively high operating speed. More than 1 meter per second is pretty much the norm. There are certain types of robots which are called high-speed pickers, where speeds of up to 10 meters per second is not unusual. Precision. Most industrial robots are capable of performing with a repeatability of less than 0.1 millimeters. On the smaller ones, typically you can get down to 0.025, 0.035 millimeters in terms of repeatability. Robots of this type are nearly always installed by professional robot integrators. If the thought of integrating robots is quite daunting, there is support available from BARA. If you get onto the BARA website, then it's possible to download how-to guides. There are white papers on various aspects of robot operation. Also expertise and advice. There is a listing of independent consultants who are available for advice. There is also a new scheme which has recently been introduced by the BARA in collaboration with the RIA, the Robot Industries Association, which is an American-based organization. So we've collaborated with them to introduce the certified scheme for robot integrators. So now we've gone through some of the background to robotic systems integration. How do we actually start the process? Firstly, I would suggest that you clearly define the objectives. What do you want to achieve? Is it to increase throughput, improve quality, reduce labour and costs? Or is it, as has happened to me, that you just want a robot to show your customers that you're a go-ahead company because you're automating? Next step, prepare a clear and concise URS, or user requirement specification. In it, include what your objective is, where is the system to go. Do you have layout drawings of the factory? Can you show clearly where it needs to fit in? Full details of your product, all the variations you could think of, both now and try to identify future requirements as well, if possible. Clearly identify what operations need to be performed. Look at the speed of throughput. How would you measure it? Is it tons per hour, items per hour, items per minute? This is your specification. Do what you want in it. Also include things like preferred suppliers. Who do you generally use for control system hardware and software? Is it Siemens? Is it Allen Bradley? Is it Omron? Is it Mitsubishi? Do you have a preferred supplier for mechatronic components such as pneumatics and air cylinders, valves, that kind of thing? Do you have a specific requirement for electric geared motors? Do you prefer David Brown or SEW Eurodrive? Do you actually have a preferred supplier of robots in mind? Whatever you can think of, whatever you think might be important or not important, get it down in the URS. It's a really, really crucial document. Once you've done that, you can then start looking around and inviting integrators to tender for the project. Perhaps considering using BARA as a source of finding a potential integrator. Remember the certification scheme. Once you've gone through the process of talking to suppliers, they will then go away and produce a tender or a quotation. What you need to do then is evaluate and compare the different proposals, check it against the URS. Does it meet all the requirements? Have they ticked all the boxes? Have they taken everything into account? Look at any feasibility studies in detail that they've produced. Look at the CAD layouts, ideally those with 3D, to allow you to look at it from all angles. See how it interacts with any existing equipment. Is there enough space available? Have any simulations been done showing the robot operation? One thing you can do, perhaps in advance of this, is actually search the web, look for similar applications. YouTube is an absolutely fantastic source of ideas and inspiration. There's every possibility that what you are trying to do is not unique. It may well have been done before. Then the difficult task, select the supplier and issue a purchase order or supply contract. But don't forget, whoever you choose, you've got to be living with them and working with them for possibly 6 months, possibly longer. Select somebody you can feel you can work with. There's got to be good chemistry there, a good relationship. Yeah, money. It makes the world go round. Cash flow is everything. So be prepared to make a deposit or down payment as per the contract terms. You will find, I would think, that no integrator will actually start working actively on a project until I've received that first down payment and it's cleared in the bank. I personally have learned from bitter experience that you can waste a lot of time doing work up front on the promise that the deposit payment will come. I've actually been caught out, and it's not a nice experience to have spent many hours working on a project you were promised only to find then it was cancelled. So now the first magical milestone of the project has been reached, i.e. the robot integrator has been selected and the purchase contract has been placed. What will the integrator do next? Firstly, acknowledge receipt of the purchase order or the contract. Raise the invoice to cover the agreed deposit. Absolutely key for cash flow. And also it proves absolute commitment on behalf of the customer. I suggest then that a project team is put together within the integration company. The customer site is then visited to confirm where the system is going to be located and carry out a thorough in-depth survey. At the quotation stage, there is never the opportunity to do this. Yeah, it's very important to fully understand any existing processes that the end user has and how they will be integrated or interacted with. The better the understanding of this, the better the system will be. Then likely you'll go back, confirm the concept layout and agree it with the customer, having taken into account any further detail found on the site survey. Starting next, carry out the detailed design process. So the team of mechanical designers, electrical controls engineers, robot programmers will come together. The mechanical layout will be done by the design engineers, checking of course that it does conform with the URS document. Working closely with the mechanical designer, the electrical control guys will get a much better understanding of how the system works, and then they'll be able to generate an FDS or functional design specification. From this, they'll be able to specify all the electrical components in the system, any elements that are required for sensing, any mechatronics components which are required. If you're fortunate enough to have virtual commissioning software, then a digital twin simulation will be able to be produced. This is a fantastic tool and is really the way forward. And in amongst all this, the robot programmer will be working. It will get a really good understanding of what the system is supposed to be doing. It will work through the FDS, and then from that start generating the robot program. And what he ought to be doing then is generating a simulation of the process. This is an indication of basic robot simulation, and what was found on the first iteration of the simulation is that the robot wasn't able to keep up with the rate at which the product was arriving. Not a good situation to be in. However, with a bit of lateral thinking, it was found that by modifying the process slightly, they were able then to perform the operation and have spare time as well. And this was done simply by allowing trays of product to arrive. Instead of treating them singly, when the first tray got to this point, it was lifted, second tray comes underneath, then 2 trays are transferred into the robot cell. Robot picks up 2 together, places one, returns back to pick up the next 2 coming in. By doing that, it saved a massive amount of time in robot movement, particularly when at this point the robot needed to reach a long way and also reach quite high. So obviously that absorbed quite a bit of cycle time. So robot simulation proved to be the winner in that situation. Let's see it again. There, you can see the robot's got waiting time. And between placing 1 and placing 2, it just saves all the time having to repeat the cycle. This is a slightly different application. What we have here is products arriving on this green conveyor, travelling from left to right. It's arriving from a process which is quite random, which is why the products which are shown on there are scattered. What we have is a camera. What the camera does, it identifies where each product is on that conveyor. It then works out X and Y coordinates for it, but you will notice the conveyor will be running from left to right, so therefore the position of the product is actually changing in the direction of travel. So to overcome that, running on the conveyor belt is a digital encoder. What this allows us to do is track the speed of the conveyor belts, and then as time passes we know the exact displacement of the product. So what the overarching control system can do then is take the data for the position, work out the time and the speed, distribute that information to the 3 robots. The system then decides which product is picked by which robot and placed into which position on the second conveyor, which is also running left to right. So what is actually happening is an array of product is created in known positions. This conveyor is also being tracked with an encoder, so that this final robot can pick a complete array of product and place it into a packaging machine. This simulation is actually running in real time, so the speed of the robots is extremely representative of what was actually seen in practice. So the output from robot simulations can be very, very useful to actually confirm that the concept is correct and will work properly in practice. What you will find is that every robot manufacturer does have simulation software which is available for their integrators. Moving on, we'll then get to a stage of signing off the design and bringing about a design freeze. This may well trigger another stage payment with the end user. Once the design has been finalised, we're then in a position to place orders for third-party equipment, for example the robots. However, on some relatively short lead time projects, it may be necessary to actually place orders for some third-party equipment before the design freeze. Next stage, we should be able to release detailed drawings for manufacture of components and other sub-assemblies. One absolutely crucial thing which must take place is regular internal design reviews. Project managers should be keeping tabs on things, making sure that everything is running smoothly, the design is progressing to the point where it does fully conform with the URS, and yeah, making sure everything else is absolutely on track. Equally, if possibly not more important, is to continue having regular project reviews with the customer or the end user. Ideally, they should have appointed a dedicated project manager so that there's an absolute continuity of communication. As time passes by, components will be manufactured, fabrications made, systems painted perhaps, and it will get to the point where it's possible then to start assembling the system mechanically. Again, there may be a payment due triggered by starting to assemble. Mechanical build continues. Then you get to the stage where electrical wiring can be put in place. Install the robots. Once we've got power on, you can then start to calibrate the robots. Start testing PLC programs and debugging them. Then get to the stage where robot programs can be tested and debugged stage by stage. Don't forget, in parallel and in the background, there will be operating procedures to prepare, manuals to produce, documentation to keep on top of. Then you'll get to the stage where an internal pre-delivery inspection can be conducted. Here, you've got to make sure that the system is conforming to the performance requirements of the URS, that the FDS for the control system is being adhered to. Crucial is doing a full risk assessment and safety check to ensure that the system does fully comply with ISO 10218 Part 2. Once everything is satisfied, it'll be the time to invite the customer along to conduct their pre-delivery inspection. Again, what they will be doing is a full performance check against the URS, and if everything is satisfactory, they'll sign off the system when it meets the specification. I would fully urge you, do not ship any system out of your works until it's been 100% satisfied. Prepare for shipment. Is it UK? Is it overseas? Is it land transport? Does shipping need to be organised? Does it need to be fully packed for export? What documentation is required to accompany the shipment? Once that's organised, it'll be time for an installation team to prepare the customer site, check that services which should be provided are provided or will be provided in time, they're in the correct location, check that any works which needed to be done have been completed. Then start the mechanical installation on site, followed closely by the electrical first fix, getting trunking, conduit, cable tray or basket in place so that the second fix can be done. Get all the cables connected, connect utilities, I/O check. I/O check is obviously very important. Make sure that all the cables are connected to the right field devices, that photocells, proximity switches, other sensor devices are actually functioning, and more importantly, actually triggering the right inputs on the PLC. Equally, check the outputs. As an output is triggered on the PLC, does it actuate the correct field device? Install and calibrate robots. Yeah, it's highly likely that the robots would have been installed during the mechanical installation, but certainly calibration can only take place once utilities are connected and you've got power to the system. Bit by bit, start doing test runs until you achieve the required performance. Big milestone, go live in production. Check that any certification is in place. Does it need to be CE? Is it been installed in the EU? UKCA for UK installations. Has the customer looked at pure certification? Then, once everybody's happy with the performance, installation acceptance and sign off. Final milestone, payments to contract. I realise that in the last few slides there's been a lot of information put across. There are a lot of stages to a project of this nature, and whether it's an installation for 1 robot or 50 robots, the process will still be the same. Each stage needs to be gone through. Summarising, select the project, prepare URS or specification, select the integrator with care, absolute care. If at all possible, keep the first project simple. I like the KISS principle. It's a good way to start. Constantly monitor both internal and external. Is everything going to plan within your company? Is everything going to plan with the customer? Keep the project managers talking. Monitor, monitor, monitor. Absolutely crucial. Don't be afraid. You've got to do your first integration project at some point. There are sources of assistance available. Don't forget, BARA can be a good point of contact. Thank you so much for listening today. I hope it has been useful and informative. And if you've got any questions or queries at all, please do not be afraid to get in touch with BARA. Thank you.